For this lesson on linear inequalities, I've drawn a number line and I've labeled 4 different numbers, and since none of them are equal, we can use a different symbol to compare them. So if you look at, let's say, -2 and 3. So I'll mark that with blue. So here's -2. It's to the left of 3 on a number line. This is our way of saying that -2 is less than 3 using this symbol. Likewise, if you're comparing 4 and 0, I'll mark those in green. So here's 4. This is 0. 4 is to the right of 0, so clearly 4 is greater than that number. So this is the idea of an inequality, using not equals, but these other symbols to compare things. In example 1, I want to just graph what these two statements mean on a number line, starting with x less than or equal to 5. Okay, I'll draw a number line and mark a few values on here. So we'll start at, let's say, 0, 1, 2, 3, 4, 5. And then go maybe -1, -2, -3, -4, -5. So when we say x is less than or equal to 5, I'll start with the equals part of it. X is allowed to be 5, so I'll put a circle there. But I just want to include every number that is going to be to the left of 5. So like, for example, is 4 less than or equal to 5? Well, it isn't equal, but it's certainly less than, so I can include that. And the same thing goes for 3 and 2 and so on. So this value and this one, everything to the left of 5 works. So I'm just going to start at 5 and just trace over the number line and put an arrow going in the other direction. This is how you could graph this inequality on a number line. It's just telling you all the numbers that work in x is less than or equal to 5. So likewise, for -4 is less than or equal to x, I'll start by just drawing a number line. Let's see, marking a few values on here. So 0, -1, -2, -3, -4, and then 1, 2, 3, 4. I want to highlight all of the numbers that make this inequality a true statement. So you can't use -4 this time. That does not work. But if you try something like -3, since -4 is less than -3 is a true statement, I do want to include -3. And the same would be true for -2 and -1 and so on. So we get all the values going to the right. You can go right up until you get to 4. So I'll just put an open circle, meaning I'm not actually including -4, just everything that is to the right of it. So on the number line, this is the solution of -4 is less than x. For example 2, I want to solve the linear equality 5x plus 8 is greater than or equal to 3x minus 4. So the goal is to find all values of x that make this thing a true statement. So this is harder than in example 1 because, well, it's not as obvious. You'd have to make a lot of computations to figure out what works. But the good news is you can treat this a lot like an equal sign as opposed to a greater than or equal to sign. What we can do is add, subtract, multiply, and divide to both sides of this inequality to reduce it to having x on one side and a number on the other. So here's what I mean. To solve this thing for x, I'm allowed to, let's say, subtract 8 from both sides of this equation. So you could start by saying, okay, I can decrease both sides by 8. And if I do that, I get 5x on one side. I get 3x minus 12 on the other, but you still have greater than or equal to. If the left side is greater than the right side and you drop them both by the same amount, greater than still has to be true. So continuing in this way, okay, let's move the x's to the left side. So I'm going to subtract 3x from both sides. Now if I do that, on the left I get 2x. On the right, I just get -12, and it still is greater than or equal to. So for the same reasoning where, okay, this was greater than or equal to this, I decreased both sides by the same amount, so greater than still holds true. For my last step, I'm going to now get x by itself by dividing both sides by 2. And since this is bigger than this, if I cut those both in half, I still get greater than. So divide by 2, divide by 2. I have x is greater than or equal to negative 6. So expressed in this way, it's a lot easier to see what the answer is. You could draw a number line. I'm going to just put, this time, only negative 6 on here. And I'm including negative 6. And I want to choose stuff that is greater than or equal to negative 6, which means I'm going in this direction. So I'm going to shade this side of the number line. So this is a visual way to represent the answer. You could say x is bigger than or equal to negative 6, or on a number line, you're starting at negative 6 and going to the right. So this is it for the example, but I would like to solve this a different way because there is something that can go a little bit wrong. So I want to start over at the beginning. 5x plus 8 is bigger than or equal to 3x minus 4. So this time I'm going to switch it around where I'm going to subtract 5x from both sides as my first step. So I'll start by subtracting 5x. I get 8 is greater than or equal to, I get negative 2x minus 4. I would now add 4 to both sides. So I get 12 is greater than or equal to negative 2x. And this is where a problem occurs. To solve for x, you'd have to divide both sides by negative 2. On the left, you get negative 6. On the right, you do get x. But the inequality will change direction if you divide both sides by a negative number. So this is the only thing to look out for. This symbol changes because we divided both sides by a negative number. We can think of that as a rule. So I've jotted this down off to the side here. It's the only thing you really would have to watch out for. So you can treat this as it were an equation, adding, subtracting, and multiplying both sides by the same amount, with the exception being anytime that you would do this with a negative, multiplying or dividing both sides by a negative, you would have to change the direction of the inequality. And for the final example, same idea as example 2, where I want to find the values of x that make this inequality true. I'm not going to graph it on a number line. I just want to see what the solution is in terms of x. So if I'm treating this a lot like an equation, my approach is going to be to cancel the fractions. So I'm looking across here and seeing, well, I can use as a least common denominator. I have a 3, a 2, and a 6. Multiplying both sides by 6 will cancel every single fraction. And 6 is a positive number, so therefore it's not going to change the direction of my inequality. So if I write this out, on the left side I'm going to multiply by 6, or if you'd like 6 over 1. That's multiplied to the left. And I'm going to do the same thing on the right, multiply by 6, or 6 over 1. If I do this, I still get that the left side is greater than or equal to the right side. And now I'm just going to copy down both sides. Okay. So if I distribute that 1/6 into the parentheses, I get 6 over 1 times 1 over 3 times x minus 4. I get plus 6 over 1 times x. You could place that over 1 if you'd like to. It still is greater than or equal to. On the right, I get 6 over 1 times 1/2 x minus 6 over 1 times 1 over 6. If I go through and cancel any common factors, I get 3 goes into 6 twice. I move to the right and see, okay, 2 goes into itself once, it goes into 6 3 times, and then it goes into 6 once at the very end. So all this becomes 2 times x minus 4 plus 6x is greater than or equal to 3 times x minus 1. So all the tricks we had for linear equations apply here as well. The exception being if you have a negative that you're multiplying or dividing to both sides. So to complete this problem, let's see, starting on the left, I'll distribute the 2. I get 2x minus 8 plus 6x is greater than or equal to 3x minus 1. Okay, so now I have 8x minus 8 is greater than or equal to 3x minus 1. I think I'll subtract 3x from both sides. I have 5x minus 8 is greater than or equal to, I just have negative 1 on the right. I can now add 8 to both sides. I'll continue my work over here. Okay, I get 5x on the left. That's greater than or equal to 7 on the right. Okay, I have to divide by this 5. It's a positive number. Therefore, it's still just x, and that's bigger than or equal to 7/5. And this is my final answer.